Hello everyone, this is Puya. This lecture is about tree data structure. So far, all the data structures that we have seen so far and abstract data types that we have seen so far are linear structures, arrays, linked lists, decks, queues, stacks, all of them are considered linear data structure. Now, trees are considered non-linear data structure. Tree is a category, a subcategory of general data structure called graph, where we have like nodes and they get connected to each other through edges. And the applications of tree, like they have like many real world applications in different industries, such as like in networking, communication, roads, airline routes, in arithmetic operations, in organizational charts, file structures, and etc. So in today's lecture, we're gonna see what a tree is and we get familiar with some of the terminologies used for trees. So in nature, the natural view of a tree is basically something that has a root at the bottom and it has some branches and it has some leaves at the end of the branches. In computer science, it's basically the upside down version of what we are used to in nature. So the root is basically at the top, and through some branches that we call edges, we go to different nodes, and this like we have like more edges, and eventually we get leaves at the end. So as previously mentioned, arrays, linked lists, stacks, queues, decks are considered linear data structures. Elements are arranged in a linear fashion, means that we have a one-dimensional representation. However, tree is a non-linear data structure that is used to represent hierarchical relationship between elements, right? So we have different hierarchies, which we call levels, and elements are arranged in a non-linear fashion. So you can see that we basically have two dimensions, right? So like it's a two-dimensional representation. It's not a linear data structure. In computer science, a tree is an abstract model for a hierarchical structure. So it can be, for example, a family tree, or it can be a taxonomy, or like it can be an organizational chart. It consists of nodes with a parent-child relationship and a set of directed edges. So these blue rectangles that we have here in this tree, they're considered nodes of the tree that basically contain the key element value that we want to store. And they get connected to each other through some edges that are directed. Okay, so the direction goes from top to the bottom, right? And the nodes that gets connected, they have a parent-child relationship. So here, for example, this node is parent for these three nodes. These three nodes are considered children of this node. So like anytime we have a connection between nodes, we are basically establishing a parent-child relationship, and it's a directional relationship. It's a directed connection. And as mentioned earlier, applications of trees can be, for example, in organizational charts or file systems, and we're going to see more applications throughout this course. We consider trees that are rooted and they only have one root, right? So we only have trees that has one root, and a rooted tree has the following properties. So one node is distinguished from the other nodes as the root, and this is the node that doesn't have any parent, right? So the node that doesn't have any parent is considered as the root, and it's going to be at the highest level of the hierarchy. Every node, let's name it C, every node C except the root is connected by an edge from exactly one other node P. Okay, so every node has only one other node P that is connected to from the higher level. So every node has only one parent. Node P in this case is the parent, node C is the child. Okay, so just remember that every node has only one parent. However, each node can have multiple children. Okay, a unique path traverses from the root to each node. So this is a very important property. There should be a path from the root of the tree to every other node in the tree. The number of edges or connections that must be followed is the path length. So if we go through one node to another node, right, the sequence of edges and the nodes that we pass through is basically it's a path, and the number of edges or the number of connections that is in that path, it's called the length of the path. So as a summary, a tree is an abstract data type that's directed, right? So it is like a hierarchy that goes from the topest level to the lowest level. It's directed, and it's acyclic. It means like there are no loops or there are no cycles in this data structure, in the structure of linked nodes. Directed means that has only one way, there are only one-way links between nodes, and two vertices are connected by exactly one path. So we can have multiple paths between two nodes. And acyclic means that no path wraps back around to the same node twice. So there are no, basically it means that there are no loops, there are no cycles. So again, just like let's do a review of the definition of tree. A tree satisfies the following properties. It has one distinct designated node or distinguished node called the root that has no parent. Every node except the root has exactly one parent. A node may have 0 or more children, and there is a unique directed path from the root to each node. So for example, this one is a 3. This node with the key value 5 is the root of the 3. And you can see that there are no cycles here, there are no loops. And from the root node to every other node, there is a unique path. This is the unique path that goes to 3. This is the unique path that goes to 2. This is the unique path that goes to this node. Another unique path that goes to 1, a unique path that goes to 6. So this is a tree. And you can see that every node has exactly one parent, but the nodes might have 0 or multiple children. For example, this node, this node, this node, this node, they don't have any children, but this node has 3 children. This one has 2 children. This is not a node. This is not a tree. You can see that, I'm sorry, this is because we have basically we don't have a unique path from this node to this node. We have actually 2 paths, right? And you can see that this node actually has 2 parents. So this is not considered a tree. This is also not a tree, right? Because if we consider this node as the root, there is no path from this root to the node that contains the element value 1, or to this node that has the element value 6. Okay, so that's the definition of a tree. Again, like this is a tree, this can be a tree, these are not trees. Okay, so like you can see that like we have a cycle here, like basically this is not a connected set of nodes. Here, like we don't have unique path between B and E, we basically have a cycle, right? So these are examples of graphs that are not trees. Nodes that share the same parent are called siblings. Okay, so for example, in this case, 5 and 7 are siblings, 2 and 6 are siblings, 5 and 11 are siblings. A binary tree is a subcategory of trees in which every node has maximum 2 children. So it can only have 0, 1, or 2 children. So this is like the definition of binary tree. Okay, just pay attention here. It says like maximum 2, not exactly 2, maximum 2 children. So let's look at this one. Is this a binary tree? Yes, it is, right? Because you can look at like every single node here, right? They either have 0 children, right? This one has 1 child, and this one also has 1 child. These 3 nodes have 3 children. So every node has maximum 2 children. This is also considered a binary tree. Is this a binary tree? No, it's not a binary tree because this node has 3 children. Okay, so that's what a binary tree is. In some textbooks or like some videos, there is an alternative definition of the trees. That's a recursive definition. Okay, so the recursive definition of a tree is that a tree is either empty, like it means that it has no nodes, we call it an empty tree, right? Or it has a root node that contains data, right? So the value that we are interested in, and it has a left subtree and a right subtree, right? This is like the recursive definition, sorry, for a binary tree. It's like we have like only 2 left and right subtrees. Okay, so it has a left subtree and a right subtree, right? It might not have like left subtree or not right subtree at the same time, might not have any of them, right? So the left and or right subtree could be empty. Okay, so let's say that in this case, right, this is the root and this is the left subtree of this node. This one is the right subtree of this node. Same thing for, like, if you look at this node, this is the left subtree of the node that contains the data 7, and this one is the right subtree of this node. The same thing here, they can look at 5. It doesn't have any left subtree, so it's empty, right? The left subtree is empty, but the right subtree contains this one. And we can do that like for these nodes as well. Like you can see that like this one doesn't have any left or right subtree, right? Both of them are empty. This one, the left subtree is only the node that contains 5. This one, the right subtree is this node. And the same thing for the other nodes. So that's what the left subtree and right subtree are. Some of the definitions that we like saw some of them before. A node is the main component of any tree structure. It stores the actual data and is linked to the other nodes. Okay. Parent is the immediate predecessor of a node. Just be careful that later on we use this term for another application and has like a slightly different meaning, right? In this case, immediate predecessor means that basically it's at the like immediate higher hierarchy level of the node that we are interested in, and it's connected to it. Immediate successor of a node are called its children. So like in the hierarchy level that we have, the nodes that come um, after a node and it's connected to them, and at the lower hierarchy and an immediate lower hierarchy are called the children of the node. Like if you have a binary tree, like the child node at the left side is called the left child and the right side is called the right child. Root is a specially designated and distinguished node that has no parent, and leaves are the nodes are the nodes at the end which do not have any children. They're also called terminal nodes or also called external nodes. So for example, in this tree, 2, 5, 11, and 4 are the nodes that have 0 children, so they are the leaves of this tree. Okay, they are the leaves or terminal nodes of this tree. They're also called external nodes. The other non-leaf nodes are considered interior or internal nodes of the tree. A link or an edge is basically a connection or a pointer to a node in the tree. It's a line that's drawn from a node N of tree to its successors, to the nodes that come after it in the hierarchy tree. A path is a sequence of consecutive edges that connects two nodes. The length of path, it's basically the number of edges on the path. Okay, so let me show you an example here. So for example, in this tree, this is one path from 2 to this one, from the root to this node. This is one path, right? And the length of this path is 2. Okay, there is also like a path from this node to this node, right? This is the path, right? And the number of edges that we pass through to get from root to the node that contains 11 is 3. So the length of this path is 3. Okay, you can also like see like there is a path from this node to this node, and the length of this path is 2. Level. Okay, so level is the rank of the hierarchy, and we consider the root node to be in level 0, right? So like the level 0, it's the roots level, so basically the highest point in highest level in our hierarchy, right? If a node it's at level L, its children are going to be at level L plus 1, and its parent is at level L minus 1. Okay, so the level of the nodes goes from 0 upwards, like as we go through the hierarchy, as we go down through the hierarchy, and it's going to be incremented one at a time when we go through different levels. Tree height is the maximum number of nodes that's possible in a path starting from root node to a leaf node. Okay, so or like maximum number of edges that we pass through to get from the root to a leaf. Okay, so we also like have a concept of the height of a node that we're going to see later. Okay, so let's just like we're going to discuss the tree height later again, right? So just keep that in mind, that it's going to be the longest path, the length of the longest path from the root to a leaf. Okay, so that's called the tree height. Degree of a node, it's the maximum number of children or number of children that we have for a tree. And siblings are the nodes that share the same parent, that have the same parent. Okay, so the two important concepts that you have to know for a tree is the level of a node, also called the depth of a node, right? The level of a node or depth of a node is the length of the path from the root to that node. Okay, so obviously the root has level 0, right? And B and C here, like the length of the path from the root to B is 1, so B is going to be at level 1, C is also at level 1, D, E, F, G are at level 2, H, I, J are at level 3, and K is at level 4. Why is it at level 4? Because the length of the path from the root to K is 4. You can see that we go through 4 edges to get from A to K. Okay, so that's what the level or depth of a node is. Height of a node is the length of the longest path from that node to a leaf node. Okay, so the length of the longest path from that node to a leaf node. Let's look at, for example, C, right? So there are paths from C to I, which is a leaf, to K, which is a leaf, to F, which is a leaf, and to G, which is a leaf. The path from C to I has the length of 2 because we go through 2 edges. So the length of this path is 2. The length of the path from C to K is 1, 2, 3. Okay, and the length of path to F is 1, the same thing for path from C to G, right? It's also 1. So the longest path from C to a node is the path from C to K, and the length of this path is 3, so the height of C is 3. The height of this node is 3. What is the height of B, of the node that contains B, right? So B only gets connected to one leaf, and the length of that is 2, so the height of B is 2. Okay, what is the height of E, right? E gets connected to 2 leaves. One is containing I, the other one contains K, right? The longest path to a leaf is the one that goes from E to K, and the length of this one is 2. So the height of E is 2. Okay. What is the height of A? The height of A, which is the root, right? We have to see like how many leaves we have. We have 1, 2, 3, 4, 5, right? So there are 5 paths from this node to a leaf, right? So this one has the length 3, this one has also the length 3, this one has the length 4, and this one has length 2, this one also has length 2. What's the longest one is the one that goes from A to K. So the height of this node, the root, is 4. Okay, the height of a root is also called the height of a tree. So like this definition that we mentioned here, it's like the height of the tree is the height of its root. Okay, it's also equal to the depth of the deepest leaf. Right, you can see that here. This is level 4, right? So this 4 is going to be basically the height of the tree as well. Okay, so the deepest level, right, has the same value as the height of a tree. If we have an empty tree, by definition, we consider the height of that tree minus 1. Okay, if you only have one node in the tree, right? One node in the tree, the height of it, it's going to be 0. The height of it is going to be 0. We already mentioned about the path. A path from node n1 to nk is a sequence of nodes such that I is the parent of ni plus 1, right? So like here, for example, like there's a path from A to Q, it's going to be A, E, J, Q. Or we can just like specify it by the edges that we go through, right? There is also like, let's say, a path from F to K, right? Or from E to P, right? E, J, P. The number of edges in the path, it's called the length of the path. A length zero path is a path from a node to itself. Okay, so like if like that basically means like we're going from B to B, for example. That's length 0. Sorry. There is always a unique path in a tree from root to any node, right? The length of this path, it's called the depth of Ni. Like we already mentioned level or depth, right? So like that's just like basically repetition. Thus the root is at depth level 0, at depth 0 or level 0. The height of the tree is the height of its root node. The depth of a tree is the depth of its deepest leaf node, which is going to be the same as the height of the tree, right? So what is the depth of this tree, right? What is the deepest leaf, right? In this hierarchy, in this tree, it's either P or Q, right? They have the same level or the same depth, right? So what is the depth of this one? This is level 0, level 1, level 2, level 3. So the deepest depth is 3, level 3. So the depth of this tree is also considered 3. So as its height, because the height of it is basically the, I'm sorry, the length of the path that goes from A, the longest path from root to a leaf, right? That's going to be either the path that goes from A to P or from A to Q, right? And that the length of them is 3. Degree is the number of subtrees of a node or the number of children of a node, right? So for example, here, degree of this node is 1, degree of this node is 2, degree of this node is 3, and so on. And the leaves, of course, they have degree 0. A leaf is a node with degree 0 or like with no children. Internal or interior nodes are non-leaf nodes. So the nodes that have a degree greater than 0, so like they have either one child or more than one child. Siblings are the nodes that have the same parent. Size of a tree is the number of nodes in that tree. So here, like you see that we have 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10. So, or like the better way of counting the nodes is 1, 2, 3, 4, 5, 4, 5, 6, 7, 8, 9, 10. So we have 10 nodes. So the size of this tree is 10. These three pictures show the concept of depth and height of nodes. You see that, or depth or level, right? This is level 0 or depth 0, level 1, level 2, level 3, and height are going to be the height of this one is 0, the height of this one, the height of this one is 1, the height of this one is 2, and the height of this one is 3. Okay. Excuse me. Okay, so you can see like the difference between depth and a height. Okay, so like again, like this definition is very important. Height of a node is the length of the longest path from V to a leaf. The length of the longest path from that node to a leaf node. Okay, so what is the height of these F, G, H, I? They're all 0. They're all 0. Okay, they're all 0 because there are leaves, right? What is the height of this one? It's the height of this one is again, like if we just like look at the length of the longest path from that node to a leaf node. So like for this one, right? For this one, this can go to 2 different leaves, right? So the longest path to a leaf is the one that goes from E to K. So the height of this one is 2. right? How about the height of this one? Is only 1. How about the height of this one? It's 0. How about the height of this one? Is 1. And the height of this one is basically the length of this path that goes from A to K, so it's 3. Okay, so pay attention to the difference between height and depth. And depth of a tree is the same as the height of a tree is the height of the height of the root, or it's the depth of the deepest leaf. Here you see the concept of subtrees, right? So like this is not a binary tree, right? So like it has like more than 2 subtrees, right? So this is one subtree, one subtree, one subtree. You see the concept of leaves, you see the concept of height, you see the concept of parent and children and degree and etc. The nodes that are filled with purple are considered leaves, or also called terminal nodes or external nodes, and the ones that are blank or like filled in with white, they are internal or interior nodes. This is root. You see like the concept of sibling. These two nodes are sibling. This is a subtree of this node of the root, and so on. How do we represent tree? A tree is a finite set of nodes together with a finite set of directed edges, right? So you see that they're directional, that they have parent-child relationship. Each directed edge connects a parent to its child, right? So you can just represent trees with like set of nodes and edges, right? So you see that like these are the nodes that we have here, and these are the edges that we have here. Okay, let's count in this tree how many nodes we have. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 nodes. So the size of this tree is 8. How many edges do we have? 1, 2, 3, 4, 5, 6, 7. So we have 8 nodes and 7 edges. This is not a coincidence. If you have a tree of n nodes, the number of edges is always n minus 1. Okay, this is because like every 2 nodes only gets connected through one edge, right? And because of that, if you have n nodes, you will have n minus 1 edges. Okay, and this again like goes through the concept of path and the length of path. We can skip that. We talked about binary tree. Binary tree is a tree for which so like all the nodes have maximum 2 children, either no children, 1 child, or 2 children. Okay, so each node has at most 2 children. We call them the left child and the right child, right? So like all these three trees are binary, right? So you can first, let's look at the middle one, right? This one has 2 children, this one has zero child, this one has 2 children, and these two have no children. Okay, and the same for the other one. So all of them are binary trees. Okay, in a binary tree, the left child, if any of the nodes, sorry, in a binary tree, the left or right child of node. Okay, so that's also like this is the concept of the left subtree and right subtree. So like here, like you see that this node, you have a left subtree and right subtree. A left subtree is the left child with all its descendants. The right subtree is the right child of the node with all its descendants. Okay, I just like have like remembered something here, that the better term that I should use here, I have to correct this. I should say like immediate ancestor and immediate descendant, right, instead of successor and predecessor, because we're going to use these terms uh, with another meaning later on when we talk about binary search trees. Okay, so it's just like remember that, so I wanted to make that correction. A binary search tree is a subcategory of binary trees. So a binary search tree is a binary tree, okay, where the value in any node n is greater than the values in every node in n's left subtree, but less than the values of every node in n's right subtree. In most conventions, we consider um, binary search trees not to have any duplicates, right? So like we consider them not to have any duplicates, right? And that's the assumption that we're gonna have in this course as well too, for the simplicity. So let's just like go over the concept of binary search tree again. So it's a binary tree, right? The value of any node is greater than the value of every node in n's left subtree, but is smaller than the value of every node in n's right subtree. Okay, I'm gonna show you what a binary search tree is, like through an example. An empty binary tree is a binary tree with no nodes. Okay, so, and we consider the height of this one -1, -1. Okay, so let's look at this example here, right? Like here, let's assume that we want to store some names in a tree, in a binary tree. Okay, so let's look at here and like we consider like alphabetical order, right? As like if you want to compare like what is bigger, what's smaller, we're going to consider the alphabetical order. So you see that here Jane starts with J, right? Okay, all the nodes in its left subtree, which is like Bob, Alan, Ellen, right? Like this is starting with B, A, and E, right? A, B, and E, they come before J, right? So that we can consider all the nodes in its left subtree are smaller than this node's value, right? All the nodes in its right subtree, right? You have Tom and Nancy and Wendy, right? T, N, and W, they come after J in the alphabetical order, right? So we can consider all of them to be bigger than Jane, right? So like all the values of the nodes on the Jane's right subtree are greater than this one. And this is true for every node, right? Let's look at Bob. See, like A comes before B, so this is smaller than this. It's in its left subtree. E comes after B, so this is in its right subtree. Ellen is in the right subtree of Bob. T is greater than N, so that's why Nancy is in the left subtree of Tom. And W comes after T in the alphabetical order, so that's why it's in the right subtree. Okay, so a binary search tree, which is a very useful tree for many application, for searching, for like dictionary application, like for everything that we're gonna do, searching, inserting, removing. It's basically a binary tree that all the elements in the left subtree of every node are smaller than that node's value, and all the elements in the right subtree of that node are gonna be bigger than the value of that node, and that's true for every node. Okay, so this is basically what a binary search tree is. These are examples of some binary trees, right? They have either 0, 1, or 2 children, okay? So let's see, like if this one is a binary search tree, right? If I look at this one, I see that, okay, yeah, for this node, B is greater than A, right? So it shouldn't be on the left subtree if you want to have a BST, a binary search tree. So this is definitely not a binary search tree. right? If the condition is not satisfied for even one node, that means that the tree is not a binary search tree. The same thing for this one. This is also not a binary search tree. Here also you can see that, let's see, like for example here C is bigger than B, but it's in its left subtree, right? So this is also not a BST, but they're binary trees. Okay, and one thing that we can also get from these three examples is that these three, they have the same number of nodes and the same number of edges. Okay, but right, the configuration of the tree is different. Let's calculate the height of this tree. The height of this tree is 2. What is the height of this one? The height of this one is 4. What's the height of this one? 1, 2, 3, 4, 5, 6, right? So they have the same nodes, but they have different heights, okay? In many applications, like we want to have our tree something like this, right? This is the ideal case, right? We want to have the smallest height as possible, right? Um, right, so that like we can just like get to every node very fast, right? But like here, like if I want to get to G, I have to go through from A to G, like I have to go through 6 edges, right? So ideally, like this is what preferable like in many applications. Like keep this in mind, and we're gonna see the concept of balanced trees, balanced binary trees, that comes next. Okay. So a full binary tree, okay, so it's a category of binary trees. Like the full binary trees are basically trees that all the leaves are at the same level. Okay, all the leaves are at the same level, and all the internal nodes have exactly 2 children. Okay, so this is called a full binary tree. Okay, so another definition, which is a recursive definition of a full binary tree: if T is empty, we consider the full binary tree. If it's not empty, T is a full binary tree if its roots subtrees are both full binary trees of height h minus 1. Okay, so if this tree wants to be full, it means that the roots subtrees, like it has to be like also full, right? So like it means that this one has to be full, this one has to be full. Okay, so like if we follow this recursive definition, we get to the actual definition, which means that all the leaves have to be at the same level, right? And all the internal nodes have to have exactly 2 children. Okay, now one thing I wanted to mention here: if we have a full binary tree, right, this is a tree that would have the maximum number of nodes, right, for like the same number of levels, right? So like here you see that this is level 0, right? At level 0 in a full binary tree, we only have the root, right? So we have like 1 node. At level 1, we have 2 nodes. At level 2, we have 4 nodes. If this continues, at level 3, we're gonna have 8 nodes. What about at level n? How many nodes are we gonna have in a full binary tree? Exactly right. So we're gonna have 2 to power n nodes at level n in a full binary tree. Okay, we're going to discuss this again in the next lecture, in the next video that I'm going to post. So we're going to see this one more time in that video, and we're going to discuss more properties of full binary trees. A complete binary tree, it's a binary tree that the leaves are at most on 2 different levels, right? The leaves are at most 2 different levels. So for example, let's look at this one. This is level 0, this is level 1, level 2, level 3, level 4. Which ones are the leaves? These 5 nodes and these other 5 nodes here. Okay, so these are the leaves. They are located at level 3 and level 4, right? So they're at 2 different levels. That's like, so it basically satisfies the first condition. Okay. The second condition is saying like the second to bottom level is completely filled in. Okay, it's completely filled in, right? So here, like this is the second to the bottom level is this level, right? Is this level, right? So it's level 0, 1, 2, 3. It's level 3, right? At level 3, in a binary tree, we can have maximum 2 to power 3, which is 8 nodes. And this one has 8 nodes, exactly. So that's what it means by having completely filled. It means like it has to have the maximum number of nodes for that level, which it does. So it also satisfies the second condition. And the last one, which is also very important, it's saying that the leaves on the bottom level are as far to the left as possible. So these 5 leaves that are at the bottom level, they are as far to the left as possible. If these leaves were like here, somewhere here, this wouldn't be a complete binary tree, right? But here, like you see that they are as far to the left as possible. Okay, so let's assume that this node didn't exist, this leaf didn't exist. Would this tree be still a complete binary tree? Like if this node didn't exist, this one? No, it wouldn't, because the nodes, the leaves at the bottom level are not as far to the left as possible. Okay, but for this one that's shown here, this is definitely a complete binary tree because it satisfies all these 3 conditions. We can define like this concept of complete binary tree other ways as well. So another equivalent definition is that a binary tree T of height h is complete if, okay, so let's look at this one. What is the height of this tree? The height of this tree is the longest path from the root. The height of the tree is the height of the root. It's the longest path from the root to a leaf, which is 1, 2, 3, 4, right? So the height of this tree is 4. So a binary tree is of height h is complete if first all nodes at level h minus 2, level h minus 2, here h is 4, h minus 2 would be 2, so like here this is level 2. So it's saying like all these nodes and above, all these nodes and above have to have exactly 2 children each, right? So like you see, this is level 2, right? Like all the nodes at level 2, they have 2 children. These ones also have 2 children. These ones, this one also has 2 children. So this is satisfied. When a node at level h minus 1 has children, all the nodes to its left at the same level should also have 2 children each. Okay, so when a node at level h minus 1 has children, all the nodes to its left at the same level has to have 2 children, right? So like this is level h minus 1, this is level h minus 1, right? Level 3, the height is 4, so this is level 3, right? Which one of them have children? So for example, this one has a child, right? All the nodes on its left at the same level have 2 children, right? So this is satisfied. The same thing for this one. This has children. All the nodes to its left have 2 children, right? So this condition is also satisfied. And the last condition is saying like when a node at level h minus 1 has only 1 child, it should be a left child. cannot be a right child, right? So here you see that the level h minus 1, right? This node has only one child, right? And it's at the left, right? So this also satisfies this condition. So all three conditions are satisfied. So you can just like follow any of these definitions. Both of them would give you the same criteria to consider if a binary tree is complete or not. Okay. A balanced binary tree. So like in many applications, we would like our trees to be balanced. What is the criteria to for being a balanced binary tree? This is a little bit um, like the specifics of it is not very firm, because there are many different versions of balanced binary trees. Okay. So as Dr. John Edgar like mentioned in his notes, a binary tree is balanced if leaves are all about the same distance from the root. Are all about the same distance from the root. Okay. Uh, so just like all about the same distance, like it's not a very exact specification, because it might vary for one category of balanced binary trees to another one, right? So, but this is basically what it means. Like all the leaves are all about the same distance from the root. Either they have exactly the same distance, or like maybe one different, right? So, um, in our class, we're gonna see a category of balanced binary trees which are height balanced, right? So we consider like balance of a tree by comparing the height of nodes. So we consider um, like a tree height balance if the height of a node's right subtree is at most one different from the height of its left subtree, right? The height of a node's right subtree is at most one different from the height of its left subtree. Okay, I'm going to talk about this in like more detail when I talk about AVL trees. And this condition should be satisfied for every single node. And sometimes we like just like find like a tree balance by comparing its height, the tree's height, compared to the number of nodes that it has, right? So for example, in red-black trees. Excuse me. So a binary tree is an AVL tree, or like AVL balance, if the height of any node's right subtree differs from the height of the node's left subtree by no more than 1. So it can be either like at the same level, so like I'm sorry, it can be 0, like the difference can be 0, can be positive 1 or negative 1, nothing beyond that. Okay. Just like some points or remarks to consider, like full binary trees are definitely complete, right? Full binary trees are complete, right? Like it satisfies all the three conditions that we had for complete binary trees. And complete binary trees are balanced. Complete binary trees, like by any of these definitions, are balanced. Okay, so like some things to remember. We're gonna see this again like when we talk about AVL trees. So this is an example so that you go through the different terminologies that we saw in this lecture. The nodes, the number of nodes, the parent-child relationship, left, right children, the edges or lengths, the root node, the leaf nodes or external nodes, level, height, the longest path, degree, and the siblings. So please go through these examples that I have in the slides. So another example that I have, and I want you to find the height of the tree, the level of different nodes, degree of different nodes, the longest path, parents of like different nodes, and their siblings and their children. You just like go through them and find all of the, these like asked variables. So we eventually want to implement this tree, right? So like the same thing that we did for stacks, queues, decks, we implemented them, right? Like we implemented them using arrays or linked list, right? So we eventually want to also uh, implement the tree. Some of the requirements that we have, right, for a tree ADT is that must be possible to access the root of a tree, must be possible to access all ancestors of any node in a tree, must be possible to access all its descendants of any node in a tree, right? So these are might be like a little bit difficult, right? It should be possible, right? Um, right, in many implementations we might not like have to implement it, right, but it should be possible to do it. Sorry. Must be possible to add a new node to a tree, like basically insert or add a new node to a tree. Like a tree can be the root node, or it can be a child, or it can be internal node, so it should be possible to do that. Must be possible to remove or delete a given node from a tree, right, together with all its descendants, or just like that node itself. It should be possible to traverse through the nodes of a tree, right? The same thing that we did in linked list, right? We traverse through different nodes. Should be possible to do traversal for a tree, and we're gonna have a separate video for different traversal methods that we have for tree nodes. Some of the member functions that we can implement if we have a tree class, right? So these are like the member functions. These are getters or accessors, and setters or mutators. So like these are some of them, not all of them, right? So you can have like constructor, destructor, copy constructor, like assignment operator, all the different things that we have seen like for classes. But other accessors and mutators that we can have is basically returning the root node of a tree, finding the parent of a node, the number of children of a node, okay, getting the key value that's stored in a node, right, return the element contained in the node, right? So um, just like making a node, like making a new root for a tree, like, or basically start a tree, right? Like this, you can just basically start a tree, make this tree consist of just a root node containing this element value. Like another one, like add a child to a specific node. I'm sorry, I don't know why this happens so often. Right, with this given element value. um, Remove a node, like set an element value for a certain node, and so on, right? So like these are different member functions that you can consider to declare and define for your tree class. Um, the the values that we store in the nodes, right, can be of any data type that we have, right? So we can have any type of objects. It can be string, it can be even non-primitive data types, it can be integer characters, doubles, and etc. Other member functions or methods that you can have, like returning the size or the number of nodes in a tree, know if like your tree is empty or not, if a certain node is root, if it's internal, if it's external, or like different things, swap elements of two nodes, um, replace the element with something else. So like there are the different things that you can do um, for a tree class. Additional update methods may be defined by data structures. Okay, one thing I forgot to do was just like wanted to show you like examples of um, complete and balanced binary trees. So for example, let's look at this tree, right? Is this one complete or full or balanced? It's none of them, right? It's not full. right? Because like it's supposed to have like two nodes here, two children here. For this one it doesn't, right? So this doesn't like satisfy the condition, so it's not full. Is it complete? No, it's not complete, because like we are supposed to have maximum number of nodes for each level up to this point, which we don't, right? So it's not complete. Is it balanced? No, it's not balanced. It's actually a very unbalanced tree, because you would see that um, like here, like you see like the height, like if like for example, let's consider the height definition that we had, the AVL balance definition we have. What's the height of the right subtree of A? The height of the right subtree of A is basically the number of edges that we go from this node to a leaf, the deepest leaf. It's like 1, 2, 3, 4, 5, 6, right? What's the height of its left subtree? It's 0. What's the difference? That's 6. Right? We said that for a tree to be height balanced, right, the difference between the left subtree and right subtree height has to be maximum 1, right? So this is not a AVL balance. Is this one AVL balanced? It is AVL balanced, right? So like you can see that this is a perfectly balanced tree, because like it's full first of all, right? It's also complete, it's also balanced. Okay, so like you know that complete, like you should remember that complete trees, full trees are complete, and complete trees are balanced, right? So this is full, therefore also complete and balanced. Let me show you another example. Maybe this one. Yeah, so let's see like if this one is full. It's not full because at this level, right, this node like doesn't have any children, right? So like, and this one has only one, so it's not full, right? And these nodes also like do not have any children, right? These ones, like they're supposed to have two children, two children, two children, and this one has to have another child, right? So this is not full. Is it complete? It's also not complete, right? Because like we are supposed to have the maximum number of nodes up to this level, which we don't, right? Because this node is supposed to have two child, which it doesn't, and this one is supposed to have another child, which it doesn't. Is it balanced? Let's look at let's see. Okay, so first of all, like this is not a good example because it's not a binary tree, right? Because this one has four children, right? So we consider AVL trees for binary search trees. This is not even a binary tree, so like we shouldn't consider this one. Okay, this is a binary tree, right? It's not a binary search tree, but let's see like if it's balanced, if it's balanced. Okay, it's not a binary tree. Sorry, this one is also not a binary tree because C has 3 children. Let me see if I have a binary tree example in the slides. No, I don't. We'll see more about balanced binary trees, complete and filled binary trees later on. Okay, this is a binary tree. Let's see if this one is balanced, right? What is the height of C's left subtree? It's 0, right? Because it doesn't have any left child. What is the height of its right subtree? It's 2. Has 2 edges to a leaf, right? So the difference between 0 and 2 is 2, right? So this shows that this is not AVL balanced. Just wanted to show you more example of balanced binary tree. This is not AVL balanced. Is it complete? Is it full, first of all? No, it's not full, right? Because this one, like, and these 3, they don't have like the maximum number of children that they should have, right? Okay, and is it complete? It's also not complete, right? Because first of all, this level doesn't have the maximum number of nodes that it should, because C is supposed to have another child here, the left child, which it doesn't. Also, this one is not as far to the left as possible, so it's not complete either. Okay. Some of the application of trees in computer science. Daniel in the class asked me about some of application of trees in computer science. So we can have many applications. So for example, file systems on a computer, folder of files in a computer like Windows or Unix, or so like these are all gonna be programmed using trees, or can be programmed using trees. Um, Family trees or organizational charts or taxonomy trees or decision trees, like in AI applications. We're going to see an example of that in the next lecture. Or like arithmetic operations, right? So like how to basically store arithmetic operations. So here, for example, you can see like how we can store an arithmetic operation, or like how to basically store cell phone numbers in an organized, sorted manner, right? So this can be a very good example of application of trees. Okay, or like organizational charts, for example, you can see that here. And this is like something that we're gonna see when we talk about binary trees and traversal through binary trees. So we're going to see like one of the examples of application of trees is basically storing algebraic expressions, right? So you remember like when we talked about stacks, we saw about infix, postfix, and prefix notations, right? So when we store an arithmetic operation in a binary tree using different traversal methods that we're gonna see later, we can just create the infix, postfix, and prefix notations. Okay, that's it for this lecture. Thank you so much, and I'll just continue this in a different video. Thank you.